Hello kids, I hope that everyone is doing very well today and that you're all ready to jump right into our next lesson in Algebra 1. But as you probably figured by now, I enjoy chocolate, so I wondered if you can tell me what is a bird's favorite type of cookie? Well, the bird is very much like Mrs. Weibel. Birds just adore chocolate chip cookies. So, that's your lame joke for the day, and we're going to go ahead and continue in our text with section 3.8, which is properties of equality. I want to re-emphasize again to you the importance of going through your text and reading it. And I know it's not thrilling reading, it's not a novel, it's not God's Word, it's not your favorite book of lame jokes, it's not your favorite action story, but there will be things in your text that I'll expect you to pick up on because there's no way that I can cover everything. But let me just go ahead and take this definition from here. We're talking about properties of equality on page 115. And it says, an equation is a mathematical sentence that states that two expressions are equal. And it does not have anything to do with the fact of the truth or error of the statement. This right here is a mathematical equation. It says 4 is equal to 8, or 4 equals 8, or 4 is 8. Was it true that 4 is equal to 8? Well, no, of course not. Just because we have a statement that says something is equal to one another does not mean that it's a true statement. And that's something that I want you to be very careful to make sure that you are paying attention to as you grow up, as you're listening to people who are outside of your circle of authority, outside of your parents, outside of your pastor, outside of trusted relatives. Just the simple fact that someone says something is equal to or something is true doesn't make it true. Now I'm going to walk into my kitchen for a minute. I want to get this little plaque that I have hanging in my kitchen, and I want you to see it if I can hold it up. And it says, never confuse the will of the majority with the will of God. And that is pretty much right along the same lines as saying that 4 is equal to 8. Just because a bunch of people say that this is the way things should be done doesn't mean it's what God is telling you to do. And furthermore, it also doesn't mean that that's what God's Word says. So as you're growing, as you're maturing, as you're learning, learn to check not only if someone says that an equation is true, that some statement is equal to one another, balance that statement against God's Word and make sure that it agrees with what He says. So, now moving on, we have simply that an equation is a mathematical sentence that says two quantities are equal. A mathematical sentence stating that two expressions are equal. And one of my kids said, Miss Betsy, why do you make M's with 3 humps? They look really weird. Well, sometimes I make M's with 3 humps. I think it's a carryover from when I was trying, when my teachers were striving with a striking lack of success to teach me how to write, stating that two expressions are equal. From when I learned cursive handwriting, I put 3 humps in there. That's all that an equation is. An equation has an equal sign. And what that equal sign acts as is sort of like your balancing point. Remember how you used to play in seesaws? Teeter-totters, I don't know what they call them now, And sometimes teenagers will go out and do the same thing. All a seesaw is some sort of a straight piece of wood, a metal, a pipe that's balanced in the middle. So when you have a seesaw that is balanced, here's the point of balance that it's sitting on top of, and here's the old little handle that you're holding on to. That's not supposed to be a person. Here's the person sitting on here. And they're both wearing bald hats, so they have no head and they have no expression. But we now have our seesaw that is balanced, and it looks like somebody's going to be offended by the fact that that's not balanced very well right there in the middle. Okay. Now, do these people weigh exactly the same? In all likelihood they don't, but they've positioned themselves in here so that the seesaw is level, it's balanced. And we're going to say that this is what an equation is. That some quantity is balanced when it's sitting on top of this seesaw. It's balanced with another quantity, doesn't even look the same. We have this other quantity, other amount, other expression. And that's a really, really important principle for algebra, the fact that when we have an equal sign with the problem that we're beginning, this is saying that the quantity, whatever it is that you have on the left-hand side of that seesaw, has the same value or the same weight in this case as the quantity that's on the other side of the seesaw. And typically it's going to look very different from each other. You remember when you played on seesaws when you were younger. Hardly ever did you see like a perfect identical twins sitting on the seesaws or balancing on them. Everybody always looked different. Your quantities are always going to look different when you're balancing an equation. But when you're balancing an equation, or actually when you're just defining an equation, this equation is, I thought I had this all set up nicely before I started. Okay, I do. I'm really looking forward to those new glasses that I'm getting so I can see a little bit better. Now, is it always going to be true that this quantity is the same as this? Like, is 4 equal to 8 like I showed you earlier? No. All an equation says is this is this. So they do have what they call false equations and true equations. So you can't just put an equal sign in between things and declare something to be true. Just like you can't say, okay, we took a vote and the majority vote says this is what God's will is for my life. This is the rightness or the wrongness of the matter. Okay? Just because you have an equal sign doesn't mean that it's true. But in the majority of the case, when we're working with our algebra, we're starting off with, we start off with the assumption that we have a true equation, and we want to use the fact that that equation is balanced, or your seesaw is straight level, to help solve something. Now let's say that we have, going back to our seesaw with Sally and Susie on it. Sally and Susie have this set up so that it's nice and balanced. And then all of a sudden, here comes Garfield the cat. Plops down on this side of the seesaw. Well, what's going to happen? Well, most of you know that Garfield is this big, honking cat. Well, immediately, seesaw looks like this now, because Garfield and Susie are down here, and I don't know who this person is. I better put Sue and Sal. your equation is out of balance because there's more weight on this left-hand side of the equation than there is on the right-hand side of the equation. So how do we get our equation back in balance? Well, up here jumps Odie. Okay, now I don't... Oh, good grief. There's Odie with his big, well, I don't even know if Odie has long floppy ears. Looks more like a bunny. And Odie has this great big long tongue. And there's, oh, good grief. So what happens if Odie weighs the same amount that Garfield weighs? What happens? Well, all of a sudden, that seesaw is back in balance because you have Sue and Garfield on one side, and you have Odie and you have Sal on the other side, and their weights are equal. So that equation has been balanced. Did they look the same? No, there's a girl and a cat and a girl and a dog. But they have the same value, they have the same weight. So what we're going to, and what did we do? The equation was out of balance. You added something to it. What did you have to do to bring it back into balance? You had to add the same value to the other side, and then your equation was balanced again. So the point of all of this rather ridiculous looking artwork that I have to say that I've reached a new low in my illustrations here. But what this is telling us is when we have an equation, we started out balanced, and that we started out balanced like this, and that equation has to remain balanced. And the way that you keep it balanced is you can add something to one side of the equation, as long as you add that same amount to the other because it balances. You can, if Garfield jumps off, what's going to happen? Well, his side's going to be up in the air again, isn't it? Well, then all you have to do is make sure Odie jumps off, and the seesaw is balanced again. If you add something to both sides of the equation, look at this. Is it true that 2 is equal to 2? Yeah, even at 9 o'clock in the morning, 2 is equal to 2. What happens if we add a 4 to both sides of the equation? Is my seesaw still balanced? Yeah. 6 is equal to 6. We added to both the same quantity to both sides of the equation. What if we subtract the same quantity from both sides of the equation? We subtract 4 from both sides. Is that equation, or is that seesaw still going to be balanced? Yeah, 2 minus 4 is minus 2, no matter which side of the equation that you're on. So when you add the same quantity to one side, you subtract the same quantity. So you, of course, know where I'm going with this. What's going to happen if we multiply? Are we still going to have the same value? What's 2 times 4? 2 times 4 is 8. Doesn't matter which side of that equation that puppy's on. Okay? The equation is still in balance. Likewise, if you divide by 4, well, I don't want to divide by 4 because I started with 2. Excuse me. Started with 2. Here. 2 divided by 4. I guess it would have been just fine, wouldn't it? I think my sneeze distracted me there. What's 2 divided by 4? It's 1/2. The point of this is that if you have an equation that's balanced, it's level, as long as you do this, perform the same operation on one side of the equation here, this side right here is heavier. You've added something to it. You add that same amount to the opposite side of the equation and it's back in balance. So, these are what they call properties of equality. And you're going to need to be able to write these for me using algebraic methods or algebraic terminology. So these are properties of equality. And all of these start out the same way. because we have to define our ground rules. So we're going to say that if A, B, and C are real numbers. Remember, the domain is the set of all of those possible values that you can use for x. We're setting up our domain here. We're saying that these variables that we're going to be using that represent numbers when we're talking about equality can be any number in the world that we're working about, that we are talking about within the scope of this class. We're not talking about imaginary numbers, but you're not expected to know about imaginary numbers anyway. So we have if A, B, and C are real numbers, then we're going to have that these following statements are true. We're talking about properties of equality. Properties of equality. What did I just illustrate for us? We have the addition property of equality. And what do you think that one says? If A is equal to B, then A plus C is equal to B plus C. You might have had difficulty with that a little bit earlier, but you see this just says if Sally and Sue are sitting on the seesaw and that C is balanced, and somebody comes and drops a 20-pound cat on the left-hand side of the seesaw, and they drop that same 20-pound cat, assuming that you can clone it, or what do they call it, a hologram that has the value of it. They clone it, they put the same 20-pound cat on the other side of that equation, it's still balanced. You've added the same quantity to both sides of the equation. They're still in balance. What about subtraction? Same thing. We're starting off with the given requirement that A, B, and C are real numbers and that the equation is in balance to begin with. If the equation is in balance, or if the equation is equal, if it's a true equation, then if you subtract the same value from both sides of the equation, you still have that equation is in balance. The addition property of equality tells us if A, B, and C are real numbers, and if A is equal to B, then A plus C is equal to B plus C. If A and B are equal to one another, in other words, if the quantities on both sides of the equation are equal, one side of the equation may look like a square, another might look like a squiggle. That's why we're using different letters here. We're saying they look different, but they have the same value. Here, this could be 4 is equal to 2 plus 3. Is that true? Sure. Or perhaps we have x is equal to 6 minus 1. They look different, but as long as they're balanced, you add the same quantity to both sides of that equation, your seesaw remains balanced, you still have a true equation. Likewise for subtraction, as long as you have real numbers. What's a number that's not real? Tell me something that you would put in here that's not a real number. There isn't anything that you would put in here. So a statement here, if you have real numbers and you subtract the same amount from both sides of the equation, then our subtraction property of equality tells us that if A and B are equal, if A is equal to B, then A minus C is the same as B minus C. And you know exactly where I'm going now, don't you? We have two more properties of equality that we're discussing. One is see how that green I just drew on my hand? This is the multiplication property of equality. And what does this one say? This one tells us that if A, B, and C are real numbers, and if A is equal to B, then A times C has to be equal to B times C. As long as you perform the same operation, same quantity on both sides of the equation remains balanced. And division. The division property of equality is the same thing. If A, B, and C are real numbers, and if A is equal to B, then A divided by B has to be, A divided by C has to be the same as B. And I don't want to do a slash like that. Let me do it this way. A divided by C is the same as B divided by C, which that truly is out of the equation, out of the view of the screen. I think that you can understand exactly what I'm saying here. Makes no difference in the value. Let me expand this just a little bit more than I thought. There, A divided by C is equal to B divided by C, whether it's set up as a rational number or whether you're using the old division sign. As long as you are dividing both sides of the equation by the same quantity, then your equation remains in balance. So let's go ahead and apply some of these rules that we've seen to some problems in our book and see what we come up with. I hope that you are seeing that these are going to be really straightforward problems. This section is not hard. We've had some that have been a little bit difficult so far. I don't think you'll have any difficulty with these. First off, though, how are we going to, let's say, let's just look at exercise number 1. In each problem below, the left side of the equation has been changed. What must you do to the right side to maintain balance? This is just sort of a little awkward to me. Is 3 the same as 2 plus 1? Yes. Now what they have done is they have said 3 plus 5 is equal to, well, obviously 3 plus 5 is equal to 8. So you're going to have to add 5 over here. They want you to look at this and say, okay, what did we do to the left-hand side of the equation? We added 5. What do you have to do to the right-hand side of the equation? Remember, as long as you do exactly the same to both sides of the equation, it remains in balance. So if we add 5 to the left side of the equation, we have to add 5. That's the sort of answer that they're looking for. Number 2. If you have x plus 7 is equal to 15, now we have x plus 7 minus 7 is equal to what? What did we start with here? You started with x plus 7. What did we do? You subtracted 7. What do you have to do on the right-hand side of the equation? You have to do exactly the same thing. So you're going to subtract 7 from the right-hand side of the equation as well. So that's what they're talking about in problems 1 through 10. And then they want you to label questions 11 through 14 if they're true or false. How do you tell if an equation is true or false? And see, this is where math is so much more concrete than things that your friends tell you. Sometimes, you know, your friends tell you something and you think, oh, that makes a whole lot of sense to me. That's a really good thing to do. That sounds like it's true. And then by the time you pray about it, talk to mom and dad about it, talk to your big sister about it, your big brother about it, you say, you know what, that really isn't true. Math is a lot more concrete. So if we have, for example number 12, we have something that says 8 plus 6 is equal to, this is problem number 12 by the way, not example, 2 times 7. You perform those operations, and because 14 is equal to 14, you have a true statement. Different operations, but it's true. Okay? All you have to do to determine whether or not an equation is true is carry out the arithmetic or algebraic operations on either side of the equation. If you end up with the same result, it's a true statement. And that is about all that I have to talk with you about for properties of equalities. And this is what we're going to be doing to come up with some structures that we'll use when we're solving equations. And it's just as simple as this. If you had x see how big this is right here? You know, somebody, you might be talking to someone and say, oh, you know, my third grader or my second grader is doing algebra. How in the world is that? I didn't do algebra until I was in 9th or 10th grade. This is an example of what they're talking about when they say algebra. You did problems like this. It was fill in the box. What plus 2 is equal to 5? Well, you learned very early on, I would hope, 3 plus 2 is equal to 5. So this is they're introducing to the kids the concept of an unknown, just getting them sticking their very tip of their little pinky toe in the water to get accustomed to what algebra is going to be looking for, because you don't know what something is and you're trying to figure it out. How you were able to solve this simple statement in your elementary school years, we're going to use those properties of other properties of equalities and some other techniques so that when we have something that's far more complex than a simple empty box, plus 2 is equal to 5, that you can solve it using true algebraic properties and principles. But you know, when somebody tells you that little kids are learning algebra, they are getting some algebraic concepts. However, they're certainly not taking high school algebra. You all have a great day. I'll talk to you again.